The next research I want to introduce about remote sensing's application urban heat island effect is the retrieval of something called discomfort index, or we simply call it DI. So it's an indicator of people's feeling on hotness of the environment. More specifically, it's about how you feel, how people feel when they're surrounded by very hot, not very hot, warm or hot air or environment, say that. You say, you just talked a lot about land surface temperature. Why not just use LST as an indicator? So the difference is that land surface temperature is only for the temperature of the skin of the surface, okay, of the Earth, of course. Specifically, when we're talking about urban study, it's about the skin of the Earth of urbanized areas. Why am I saying skin? Because surface could be very thick, right? Skin of the surface, for example, the skin of a pavement is just maybe several centimeter, okay, below the surface of the pavement and maybe several centimeter above the pavement. So that area, several centimeters below and above the surface, that area is called the skin of the surface. We usually say that it's not a very very strict concept. That is land surface temperature, but land surface temperature is not the temperature we feel when we're standing in the middle of a square in a very hot summer day, right? What we feel is our surrounding air, our surrounding the hotness from our surrounding environment. It's not surface, right? So you may say, why not use air temperature? Air temperature is okay. Usually in weather forecast, the temperature is air temperature, but this DI is beyond air temperature. It is an indicator proposed by scholars from public health. It's a comprehensive indicator related to the environment, of course, and also people's psychology. Okay, and in order to calculate this index, you need air temperature. But a retrieval of air temperature from remote sensing is very hard. Land surface temperature can be accurately retrieved from remotely sensed data, but air temperature is another thing. It's very complex. Okay, but you just need to know that DI is an index to address people's feeling when they're surrounded by hot environment or warm environment. So you can say here, we have two thematic maps showing the spatial distribution of DI within the state of Wisconsin on 2 days, right? One day in 2008, another day in 2010. Okay, and the unit of DI is also Celsius degree. Okay, it's DI can be considered as an equivalent temperature. So its unit is still Celsius degree. Again, bright areas, therefore, high DI values, which means within those areas, people should be feeling hot, and very discomfortable. And the dark areas, they are for lower or very low DI values. So this is Wisconsin, right? So maybe you not know, but most population within state, they are living to the southeast corner of the state, right? This is, again, this is Milwaukee metropolitan area. Here is Madison, and we have other several cities here. Here is Green Bay. I'm not sure about the name of the city, but you can say this is a bright area. So it's another city, another city, another city here, which means people are living there, but this area is covered by forest, by agricultural land. So you can say this area is generally in a tone of darkness, so it's dark. So if you compare these two maps, the spatial distribution of DI is similar. So in urbanized areas, DI value is high. In unurban, in rural areas, in wilderness, the value is low. And I want to show you another day. So it's August 6th in 2012. You can see that in general, the spatial distribution of DI here is similar to other two maps. But above that, you can say something wrong is here. There is something wrong here. You can say that there is haze. A layer of haze is covering the north and northwest of the state and also southeast of the state, right? Looks like there is a layer of haze is covering a very large part of the state. That is related to the humidity of the air. Okay, so in order to calculate DI, like I said, you need to know air temperature. And another factor you need to take into account is humidity. And you can say that if you compare the first two maps with the last one, for that specific day, the spatial distribution of humidity for Wisconsin, for the state of Wisconsin, was very spatial. Okay, so this part, this hazed part of the state, and this hazed part of the state, they were heavily infected by high humidity. Okay, that's the reason why that you can say in general you can tell that there is haze covering the whole state. Okay, and another thing I want to mention here is that for neighboring effect research, I used Milwaukee City as a study area, right? Here I'm using the state of Wisconsin. Obviously, previously, I was doing research at city level or say county level, but this time I'm doing research at state level. Oh, why do I change? This is something you need to do in future when you are in research or you are doing your work. It's a compromise because in order to get humidity data, in order to retrieve air temperature, I downloaded data from multiple sources and I did not find high spatial resolution data for humidity and air and other data for air temperature retrieval, which means that it's not possible to carry out this part of the research at city level or county level, because in the data I found, they were all at least at state level, which means that the whole county of Milwaukee may only occupy dozens of pixels, and that is just not enough. Okay, so I changed the scale of my research for DI to state level. Okay, and here is other several scatter plots to show you the relationship between DI and NDVI. So DI is for discomfort, and usually NDVI is for vegetation. In other words, should be comfort, right? NDVI should be an indicator of comfortness, because in summer, where do you want to stand? In the middle of a square with nothing, or under a tree, a very huge tree, and surrounded by vegetation? All of us would choose the later one because it's cooler, it feels comfortable, right? So here is the statistical results to address the correlation between DI and NDVI. So the horizontal axis for the three figures, for the three scatter plots, they are NDVI, and the vertical one is for discomfort index. You can say, I did not draw the regression model or the line, but if I draw them, it'd be like this, right? So negatively correlated. And if you compare R squared, the first two, they're okay. Okay, especially for the first day, the R squared is 0.35. It's good. You say it's very far away from 1.0. How do you say it's good? Because in statistics, when we're talking about the comparison of R squares, it's always a problem of a problem of relativity. Okay, you need to compare this value with other values in your research instead of an absolute good value of 1.0. And the second one is okay, and the third one is 0. And this is why. This is not why. This is actually the result of the abnormal spatial distribution of humidity of this day. Okay, this hazed area and this huge hazed area, or say areas covered by haze, they affected the relationship between DI and NDVI. Okay, that's a small conclusion from my research. Okay, so that's DI, and I also did something called spatial configuration of land covers and its relationship with DI. Why do I do this? Because DI is an indicator of comfortness, right? So I want to address a problem about how different land covers should be distributed within urbanized areas to make people feel less discomfortable, or to make people feel more comfortable, right? And for example, you want to distribute some trees within the city, say several hundreds of trees, okay, several hundred trees. Should I put them together to make a huge park, or should I distribute all these trees in different corners of the city to make small vegetation patches? Okay, that's a concept of spatial configuration. Okay, or should I have several hundred trees to distribute, right? Should I make a huge, I mean, patch of circle, or should I just line all these trees along a specific direction to make it a linear feature of trees? Okay, that's also about spatial configuration, but it's about the shape of your patch. Should I make a round patch or a linear shaped patch? That's spatial configuration. Spatial configuration is a very important topic in some discipline called landscape ecology, but that's another story. I just borrowed some metrics from landscape ecology to address the spatial configuration of different land covers in urbanized areas. And there is another concept you may say in future. It's called spatial composition. Spatial composition is about land cover types. Okay, trees, water body, soil. When you are asked about land cover composition, you should say, okay, within this area there are 1, 2, 3, or 4, or even 5 land cover types, and they decide land cover. Oh, they decide spatial they decide spatial composition, but how they're distributed, how they're organized within space, that is spatial configuration. Okay, so the whole state, in order to address this relationship between DI and spatial configuration of land covers, the whole state of Wisconsin was classified into 3 classes. Okay, tree, grass, and impervious surfaces. Each class forms 0, 1, or more patches within each polygon. Okay, so I sampled I sampled several polygons from both rural and urban areas in Wisconsin. And within each polygon, let me show you. Here, I have two sample polygons. On the left side is a rural polygon. On the right side is an urban polygon. And we have different colors here, okay? So green is for grass. Green is for grass. And blue is for trees. Red is for impervious surface. Okay, so of course, the smallest unit here is still pixel. And you can say there are blue patches, there are green patches, and there are red patches. Okay, I will use landscape ecology metrics to address the spatial configuration of these small patches of different land covers. And say if there is statistical relationship between the spatial configuration of patches and DI. So that conclusion, or say you will say later, there are a lot of conclusions actually. These conclusions can support the decision of city designers, city planners about how to build a city, how to distribute different land covers. Okay, so landscape metrics I borrowed from landscape ecology. For example, P-land, abundance of a glass. This is actually, you can consider this as landscape composition, abundance of a class, right? It's just like the abundance we want from LSMA. So P-land itself addresses landscape composition, but landscape ecology also uses it to address an aspect of land configuration. Okay, landscape configuration. PD is number of patches per hectare, or you can say PD is simply a patch density. And edge density, ED, edge length of patches per hectare. Okay, so should we just distribute all those trees to make sure that this patch has the longest edge, or should we follow some other principles to create these patches for trees? Okay, and LSI is an indicator for compactness of a patch. So different shapes, they have different compactness, and this can be qualified. Sorry, this can be quantified. LSI is the quantified indicator of compactness. And by the way, circle has the largest compactness. Okay. And another one is called fractal dimension. It's about the complexity of patch shape. Okay. And here is the result. For tree, for impervious surface, for grass, I calculated the correlation coefficients between different landscape metrics and DI. So here is a very large, not very large, but large enough table. I'm not going to explain all these results, and I will just jump to the conclusions. So implications on urban design. So according to the research, okay, for trees, they should be deployed in less patches with dispersed and complex shapes, which means that, let's get back to the question I asked you before. If you have hundreds of trees to deploy in the city, should you make a huge patch or make several small patches? Here is the result. Okay, you should have large patches, which means less patches, with dispersed and the complex shapes, which means do not make them very regular. Okay, you should make sure that each patch should have expanded and complex shape. Okay, so that's a conclusion from the research. And for impervious surface, this these buildings or these geographic objects covered by impervious surfaces should be deployed in less patches, just like trees, with dispersed but less complex shapes. So if you are trying to say build a shopping mall, okay, in suburban area, in order to pursue a lower DI within that area, you should make sure that that shopping mall should have a very simple shape. For example, a square, a rectangle, instead of an irregular shape with very long boundaries. Okay, that's for impervious surface. And for grass, actually does not have significant impact on heat stress. This is actually very interesting because I cannot find a very, how can I say, very sure reason for why this is a result. Because I mean, the result is that grass and DI does not have significant correlation, which means more grass, less grass, it doesn't matter in terms of DI. But my guess, because I'm not an expert in ecology, my guess is that a grass, they provide evaporation. Okay, they can cool the environment, but since maybe, okay, maybe the evaporation effect from grass is just too weak, say that, because grass is just very close to the ground, and the evaporation, the cooling effect of grass cannot significantly affect the humidity of the air, cannot significantly lower the temperature of the air. So it does not have very strong or significant relationship with DI. So less grass, more grass, it doesn't matter that much in terms of DI, discomfort index. Okay, so I think that I've introduced enough and a lot, okay, for urban remote sensing, because it is what I did when I was a PhD candidate. So this slide concludes this lecture. It's about urban remote sensing. Okay, we still have two lectures, one about water remote sensing, another one for vegetation remote sensing, and I will see you in next lecture. Okay, thank you.